So the topic today is towards intelligent 6G RAN. I'll give a short research overview of our group. And I'm Nandana Rajatheva, and my main area of interest is physical layer and also resource allocation, increasingly now with machine learning applications. So my group actually is here with several postdoctoral and senior doctoral students, and of course together with master students. And in terms of our recent research, we focus quite a lot on this application of AI and ML for radio access networks. And the projects that we are currently involved are these ISAC, ISAC2. We have also recently started this EU Korea project called 6G Arrow, and that also considers quite a lot on this application of AI into RAN. All right, so now if you look at this figure, you can see that different layers from physical layer to application layer has various considerations from machine learning, from autoencoder to machine learning as a service. Moving on, let's go through different topics that we are working on. One of the most important application or areas is this constellation and waveform designs for 6G. And on that, the first topic I discuss is this AI ML for sub-THz physical layer, which is sub-THz is needed for high bit rate systems. And on the figure left-hand side, you can see at the top the traditional communication link, and then parts of the receiver, we apply machine learning, and then parts of the transmitter as well, together with this neural receiver. So the figure on the top right shows this constellation shaping, and then followed by the neural demapper, and then there is also the second figure on the right bottom is the learned constellation pilots and the neural receiver. So this implies that we have now incorporated some aspects of machine learning into the structure. And along with that, actually, we are also working on this grand decoder with probabilistic constellation shaping following the work earlier. And there we have some results where we consider some application to get the soft information, and the performance is shown in the figure there. So the main thing is to lower the complexity and have better energy efficiency. And then we have also started some works on this spike in neural networks, mimicking biological neural networks, and these now used in our case as neural demapper. So the targets are energy efficiency and better training, and target is, or the potential is, to really have a scalable solution for energy efficiency. And you can see the performance on a particular communication system involving high order constellation, where the neural demapper has given the same performance as the baseline, but we are investigating this further. So now we move to the next topic, from physical layer to distributed MIMO, where the first one actually is to consider resource allocation side cell-free systems. Traditionally, we have solution for this with optimization approach. What we have done is to consider unsupervised learning-based model. And as you can see in these figures, the performance from, if you wish to start on the left-hand side, performance of this is quite close to the traditional optimization method. And importantly, on the right-hand side, you can see the complexity of this gradient-based control is quite high when you consider increasing number of access points. But we have shown that with this learning-based model that it stays pretty low and constant. And in a similar manner, we have also considered the minimizing energy consumption in a cell-free network. Here, the idea is to switch off access points. So the problem is that when you have large number of UEs and access points, all of them, and that leads to higher energy consumption. So the solution is to come up with an algorithm to provide this lower power in the total system. So that is the one that we have obtained here. And along the same lines, actually, when we move on to these MIMO systems, one important thing is this transmit antenna muting to allow significant transmit power savings. So the advantage is that along with the power saving, we have lower computational complexity. And then we have several topics to follow, starting with RIS systems, pre-configurable intelligence systems. The first one actually considers also the reflection modulation, where we have these subunits. So the resource allocation in these subunits, and to consider active and passive beamforming solutions, and also to adapt this framework to incorporate reflection modulation. So convergence performance on these beamforming algorithms that you can see, they are fairly good. And based on this, let us say, optimization based approach, we are also considering this applicable application to learning based RIS systems together with reflection modulation, where the objective is, of course, to minimize the bit error rate, whereas in the traditional case we have maybe higher bit error rates. So along with this, we have a couple of other studies focusing on channel estimation. So in this case, the solution again is machine learning based solution. The challenge is especially in vehicular systems where you have the Doppler shift and then we have the time varying scenario. So that the solution is to come up with this ResNet based angle of arrival prediction and come up with lower complexity gains. As you can see in the figure on the left hand side, you can see the mean square error values are lower with the proposed solution. So in a similar fashion, we also have considered channel estimation with this beyond diagonal RIS and SIM-assisted multi-user MISO systems, where the pilot overhead is considered as a case to reduce it. So with that, we have quite good performance. Now, along with all these systems, the power amplifier plays a significant role. So the important thing in this particular case is to consider the complexity reduction or to linearize this DPD actually. So we consider various methods, and importantly what we do is we propose this box-oriented or modular approach where we have the static nonlinear effects and the memory effects, so that we try to have this, as you can see, with the 50% complexity reduction is obtained. And this is actually illustrated further here. So the neural network based model for behavioral modeling and this digital predistortion of power amplifiers. So how to minimize these effects. And we have done some measurements also, and the results are shown here. And then moving on, we also considered the case of machine type communication, where you have large number of IoT devices. Actually, the main thing is to consider the base station has to identify the sparsely active devices. So we have considered several scenarios, SCMA and MUSA. The highlights are the higher probability detection with various overloading factors, and this is also a ResNet based approach in one, and also we have considered this vision based approach. So the idea is to have lower complexity. So the main thing is to see whether we can identify these users which are sparsely active. And this was also actually extended to as a multi-user detection case for this indoor factory scenario, which is a practical case when we consider, let's say, various autonomously guided vehicles, right? So that it goes through a particular path, and in this particular scenario, you can see the probability of detection with the sparsity and also the measurement. So the received power when you have line of sight, when you don't have line of sight, and the percentage of active devices is maximum 10%, as the confusion matrix shows. It detects about 10% of active devices and also detects 90% of non-active devices. So the advantages are again high probability of detection and data-driven investigation, obviously targeting lower complexity. And along with these topics, one key area that is emerging right now is sensing. So we have considered several cases for sensing. First one actually is the let's say, standard view right now of integrated sensing and communication ISAC for beamforming design in this multi-user, multi-target MIMO system, where we have this bistatic system and multi-user scenario. So especially with a high number of users, you can see the performance on the left-hand side as well. With a better signal-to-noise ratio, the performance of this target estimation is quite high, and the ongoing work involves this multi-user detection and robust beamforming. And then a little bit different to this integrated approach in the sense it is still integrated, but here we are using, let us say, radar-based approach. From radar, we move to LiDAR-based, LiDAR-aided beam prediction. We have done quite a lot of work on this one. So the challenge is when we have narrow beams in millimeter wave and sub-THz systems, how to counter these propagation issues. So we have to have these stable systems under mobility, which is pretty hard. So the current solution is there, this beam measurement prediction. What we propose is through LiDAR, we get this information to predict the beam decision. So we have a new machine learning model, and input is coming from location data from LiDAR and then pass beam decision. So we use that to reduce this BMR frequency. And importantly, with LiDAR, then we can also consider this digital twin scenario, LiDAR-aided dynamic digital twins, where you can create the scene and then process these LiDAR inputs. And then we try to emulate actually this dynamics and on top of the static digital twin, and then to see also ray tracing real time for predictive 6G applications. So the target is that we consider a dynamic scenario. And based on these discussions, because of the application of AI and ML into radio access networks, so we have joined this AI RAN Alliance recently, August 2024, and we are working on this work group 1 active there. So accordingly, we are also planning this AI RAN lab here together with the test network. You can see the other ones, 3GPP network, also NATO Dyna Center. So we try to implement the research that we have considered earlier in various topics, from the constellation shaping to digital twin to all these in some fashion in this AI RAN lab. This concludes the research overview in my group. So thank you.